In this second section of work problems from chapter 5, we will be referring to the VSEPR table. This is the table I provide for students on the test. It's slightly different. It's the same information, but in a slightly different format from the table that's shown in the textbook. Whichever one works for you is best, but know that you will want to have access to something along those lines. Note that if we point out a few things that, this is my quantity of electron domains. An electron domain, it's sort of defining, is either a bond, and note down here, it doesn't matter whether it's a single bond or a triple bond. They're each considered one electron domain. When you have a triple bond, while there are 3 bonds and 3 sets of shared electrons, all 6 of the electrons in those triple bond is between the 2 atoms. So they're all in the same general domain. That's why it doesn't matter whether it's a double or triple bond, it's still just one domain. A lone pair would be a separate domain. And then we're going to focus on the first part on just electron geometry. In electron geometry, I only care about this. So I'm going to ignore columns to the right. And then for molecular geometry, the number of lone pairs determines which column to look in. So electron geometry is only depends on total. And so it's always column 1 or column 2, second column. So it's either the zero lone pair column for molecular geometries, or it's the column that we use for electron geometry. And again, remember, these are about the central atom. So another mistake students will make when using this table is that they're counting lone pairs on outer atoms. We would not. We would only count the bonds in the lone pairs on the center atom in order to determine the electron domains on the center atom. Okay, find the electron geometry, the molecular geometry, and the bond angles. Can't do it without a Lewis structure. So first, draw the Lewis structure. I will say, typically when I'm asking about geometry to save time, I will give you a Lewis structure, but we want to get super great at drawing Lewis structures, so more practice is better. All right, valence. Carbon is 4, chlorine is 7, but there's 4 of them. 4 times 7 is 28, plus 4 equals 32. We put carbon in the middle, chlorine, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I ran out, I'm done. And now I would check octets, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Octets are okay. So now I have a structure. Now let's look at how I assemble. So in terms of electron geometry, I need total domains. And this one has 3 single bonds plus 1 lone pair, 4 domains. Oh, what am I doing? 4 bonds. I do have 4. I'm thinking ahead to a different problem. I'm just going to erase that. It's been a long day already. Okay, so I have 4 single bonds. I have no double bonds. I have no triple bonds. I have no lone pairs. So my total is 4. And then I'm going to look in column 2, the electron geometry column, row with 4 total. And when I do so, I'm going to see I get tetrahedral. For my molecular geometry, I'm going to consider lone pair in total. Well, there were no lone pairs, so that's 0. And I would move to that column. It's the same column. Still numbered the second column. So it's going to be the same, tetrahedral. Now, bond angles, I simply look it up. It tells me in the same box, 109.5 degrees. Look in column 1 for total. So where I find that for totals, it's always going to be bond angles of 109.5. Now, realistically, we've talked about when you have lone pairs, they can sort of make this a little bit smaller because the lone pair takes up a little more space. Just tell me the one off the table. All right, the second one, I first have to draw my structure. No, I have to consider the lack of electron in this case. So valence is 7 plus 4 times 7 minus 1 for the charge. All right, so 28 plus 6, let me do this on a calculator. I don't trust my math in my head. 7 plus 28 minus 1, 34. I'm going to put the chlorine in the middle because chlorine is less electronegative than fluorine. Fluorine, 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 fluorine. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And here's my 34 would be an additional one on the center atom. It is allowed. Chlorine is in period 3. So extended octets are possible. All right, so 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So for octets, all F have octets, and for the center one, I have 2, 4, 6, 8, 10. But we said it's capable of having extended octet, so 10 is okay. Again, technically, I would now put the rest of this in brackets and put a positive charge to indicate that this structure must exist with one fewer electrons. Otherwise, it's not a valid structure if I don't indicate that there is a charge. All right, same thing. Molecular geometry. Well, let's do electronic geometry. Electron. My total domains for chlorine has 4 single bonds plus 1 lone pair for a total of 5 total. And the shape for 5 total is trigonal bipyramidal. Now, for my molecular shape, I'm going to stay in row with total equals 5, but move to column that says 1 lone pair. And when I do, and I see what's in the box, I think it is seesaw. I have to go back. Yes, 1 lone pair is seesaw. And when I'm looking for bond angles, with this shape, there are 2 kinds of bond angles. Some of them are 90 degrees. The equatorial ones are 120 degrees. The axial ones are 90 degrees. Just list both of them. Two more, same problem. Let's do my water structure. We did water earlier. So I'm just showing its Lewis structure. We've already checked it in an earlier video. This one would be my electron geometry. So let's see, my center O has 2 single bonds and 2 lone pair, equal 4 total. So I go to my 4 total. So for the row, total 4 domains. And for my column, I'm going to use number 2, which is the electron geometry column. And that says it's tetrahedral. However, for my molecular geometry, move over to column for 2 lone pairs. It's still 4 total row. And that tells me that this is a bent. And my angles, I look in the original box with 4 total, and it's 109.5 degrees. SF5 with a minus charge. This one I'm going to have to draw out. We haven't done this one yet. Sulfur is 6 plus 5 times 7 plus 1 for the ion charge equals, that's 35 plus 6 is 41 plus 1 is 42. Sulfur in the center, fluorine, 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 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42. Let me double check that. So sometimes with that, I'll use a laser pointer, I'll use a highlighter and double check when I'm counting to make sure I'm counting uniquely. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, and then 42. Yes, I've got the right total. If I check, I can see on the outer atoms, all have octets. And then on the sulfur center, it has 2, 4, 6, 8, 10, 12 electrons, but sulfur is period 3. So extended is okay. So we'll allow that. All right, this is my structure. Again, because it has a charge, I should put it in brackets with a negative charge around it saying this structure has a negative charge somewhere. Alternatively, I could do the formal charges for everything, find which one has the negative charge, and mark it as negative. All right, so let's see, the electron geometry. Electron geometry. My center S has 5 bonds plus 1 lone pair equals 6 total. When I look up 6 total, that's an octahedral electron geometry. When I look at the molecular geometry, I'm going to move over to 1 lone pair column, but still the 6 total. I don't have that one memorized. Let me go back up to that one. So 6, I'm going to be this bottom row here, and I'm going to the 1 lone pair square pyramidal. Square pyramidal. Now my bond angles, don't care what my molecular geometry is. They're independent. It's only for a total of 6 that is 90 degrees. And so I'm done. Find the net dipole moments for these molecules. Remember, in the net dipole moment, this is very complex. I have to consider, one, are there any polar bonds? So delta En is greater than 0.4. We're not going to be worrying about the ionic ones, so it can be just as long as it's greater than 0.4. 2, is it a symmetrical shape? So if yes, then is it a symmetrical shape? And we have a list of 6 symmetrical shapes: linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and square planar. And if the answer is yes, are all bonds to center atom identical delta En values? In other words, are they identically polar? And if the answer is yes, then that would mean it would be nonpolar bisymmetry. If the answer is no, then it's polar. By the way, if it's not a symmetrical shape, then it's polar. If it has no polar bonds, then it's nonpolar. So there are many possible situations. I kind of have to check all of these things. It's definitely a hard problem. I'm just going to draw the Lewis structures in the interest of time. But again, it's good practice for you to draw them. CF4, say 4 times 7 is 28, plus 4 is 32. 2, 4, 6, 10, 12, 14, 16, 6, 28, 32. Yes, this is a good structure. So the first thing I want to do is determine the delta En. Again, I'm going to have my electronegativity table. So for my CBr, bromine is 2.8 minus 2.5 for carbon equals 0.3. So this is a non-polar bond. It is not greater than 0.4. For CH, carbon is 2.5, hydrogen is 2.1, 0.4. That's also nonpolar. Ties go towards nonpolar. It has to be greater than 0.4 to be polar. So there are no polar bonds. Note that I check, are there any polar bonds? The answer was no, I'm done. If it's nonpolar, that is equivalent to saying there is no net dipole. CF4, by the way, you technically could calculate dipole moments. We are not capable of doing it in this class because you have to add dipoles vectorially. That's not what we're doing in this class. So this was simply, maybe it shouldn't say find the net dipole, but it should be, is there a net dipole moments for these molecules? So to be better worded for this level of class. But I wanted to show the net dipole moment type of way of asking, is it polar or not? This would be equivalent to saying, are these molecules polar or nonpolar? So this would be nonpolar molecule due to having no dipole due to having no polar bonds. Let's do it again in the second case, but now notice that the only kind of bond I have in this structure is CF. The center atom is C. It's only bonded to F's. So in this case, fluorine is 4.0 minus 2.5 chlorine equals 1.4. carbon, C, that's 1.5. So this is greater than 0.4, so polar. So I have 4 identically polar bonds. So I do have polar bonds. So question 2, shape. I'm looking at that center carbon. Carbon has 4 bonds plus 0 lone pair equals 4 total, with 0 of them being lone pair. That shape is tetrahedral. And tetrahedral is on list of symmetrical shapes. So this would be, yes, symmetrical shape. Therefore, I keep going. Identically polar bonds. So again, all the bonds have to be identically polar in this shape, and they're all 1.5 delta En. So yes, they're all identically polar. So now we're here. These are all, the center atom has identically polar bonds, therefore it is non-polar by symmetry, which means no net dipole. Let's try another one. CO2. All right, the structure would be carbon, oxygen, oxygen. I have 4 plus 2 times 6, so I have 12 plus 4 equals 16. 2, 4, 6, 8, 10, 12, 14, 16. I chose to take an outer lone pair and to make it a double bond because from lots of experience, I know oxygen will have no formal charge if it has 2 bonds and 2 lone pairs. Additionally, I know that this carbon is going to need 4 bonds to it in order that it has no formal charge. Since it has a valence of 4, it's going to need 4 bonds. That's the only way to get 8 electrons in an octet while having no formal charge. So I quickly drew it this way. You would probably have to go through, recognize that the center carbon doesn't have octets, and start making double bonds. So here is my Lewis structure. Let's establish, are there any polar bonds? So I'm looking at carbon. Let's do oxygen is higher, it's 3.0, minus carbon is 2.5. Wait, that's not true. I think oxygen is 3.5. Equals 1.0, so yes, polar. Note that both of these would be polar 1.0. So since I do have polar bonds, I'm just going to kind of write them so I know later if I have to evaluate, are they identically polar? I have the numbers available for myself. So yes. The next step is it a symmetrical shape? Okay, the molecular shape is for carbon with 2 double bonds plus 0 lone pair equals 2 domains total. Remember, a double bond is just 1 domain. So I have 2 domains on this center carbon. 0 lone pair. So the shape is linear. And yes, that's symmetrical. So that's on my list. So the next question would be, do I have identically polar bonds? Here I look and I say, oh, look, there's only two bonds and both of them are 1.0 delta En. They are identically polar, yes. So in this case, I'm going to have non-polar by symmetry. The question asked, is there a net dipole moment for these molecules? No net dipole. Now, there are dipoles in there because I do have polar bonds. That's another word for what polar bond is, has a dipole. So there are dipoles, but there's no net dipole moment because due to the shape and being identically polar, they cancel out. ClF4, we drew this already in the shape video. Not only that, we actually determined a couple of slides ago. This had a center pair there. And we also had determined, well, let's first do polar bonds. Change color. Polar bonds. So ClF, fluorine is 4.0 minus 3.0 for chlorine equals 1.0, which is greater than 0.4. So yes, I have polar bonds. Do I have a symmetrical shape? Let's see. So my shape would be for chlorine has 4 bonds, 1 lone pair, 5 total. And if I go to the 5 total, 1 lone pair, the shape is seesaw. No, not on list of symmetrical. Note that once I get to a no here, I'm done. Now that tells me that this is polar. Yes, it has a net dipole moment. Again, once I get to a no answer, pretty much the process ends. I want to use that flow chart to determine that. But because it's not symmetrical, even though I have identically polar bonds, they are not able to cancel each other out due to not being in a symmetrical shape. And there you have it.